I will be introducing today's colloquium speaker. So welcome to this ICCUB colloquium. And so basically Professor Morgan Mitchell, first it's really nice to have him here because he will be talking about the physics of the Nobel Prize in 2022, this year. And he is an actual main character of this. So he has been working on this kind of physics for many years and he knows details and he's an experimentalist. So it's a kind of first-hand account of the kind of physics that is at the stage here. Just to give some idea of Professor Morgan Mitchell's career. So he did the PhD in Berkeley in 1999, and then he was in several renowned groups around the world, like the group of Professor Serge Haroche in École Normale Sup, by the way, Nobel Prize winner also. And he was basically at Reeds College, then in Afrem Steinberg's group in Toronto. And in 2004, among other places, by the way, and in 2004, he joined ICFO, the Institute of Photonic Sciences, which is in Castelldefels. And in 2011, he became ICREA professor. So he's basically the leader of the Atomic Quantum Optics group at ICFO, and he was the coordinator and still the coordinating of the Quantum CAT community, this Ristress CAT emergent community on quantum technologies and quantum science in the region. So he's one of the persons that is working actively to have a relevant network of all the players in the region contributing to this quantum physics. He was awarded an ERC starting grant in 2011 and an ERC proof of concept grant in 2016 and has got some prizes like the Vanguardia de la Ciencia Award in 2012, Ehrenfest Prize and Kirby Publication Prize in 2016. Just to tell you, so Professor Mitchell was the lead, the person that led the contribution from ICFO, which was actually the quantum random number generators that were used in the experiments, in the loophole free Bell experiments in Delft, Vienna, and NIST. One of them, this was in 2015, one of them carried out by Anton Zeilinger, who is one of the Nobel Prize winners this year. So it's nice to hear that these experiments were done with relevant contribution from ICFO and carried by or led by Morgan. He was also the main coordinator of a huge effort, which was called the Big Bell test, which was a worldwide experiment involving all the experiments in the world in this kind of physics to do well, maybe you will comment, but it was an experiment that was also, it has a lot of involvement also of the social, of popularization of science. So it became schools, everybody could play a game and produce random numbers, and this was used in experiments actually. And finally, he was also the co-founder of QSight Technologies, which is a company, a spin-off from ICFO that is producing and selling machines that produce quantum random number generators. So this is, as I say, he's one of the really important players in this. Let me also mention that he is also very actively involved in the Master in Quantum Science and Tech that we have here as a lecturer and also as a main driver of the initiative when we started. So it's a great pleasure to have you here. Thank you, Morgan, and the floor is yours.
Okay, thank you, Bruno, for that very nice introduction. Yes, I'm particularly proud to be associated with the Masters in Quantum Science and Technology, but Bruno is very generous when he gives me any credit. I think almost all of the credit is for him and his colleagues. Okay. So this is a Nobel Prize, which is, in fact, reasonably personal to me. When I was in my last year of university, then a professor that I had was very impressed by the work of Alain Aspect, and we had a seminar on it. We had a course which spent about half of a semester talking about all of the interpretations of quantum mechanics and talking about what had been contributed by Aspect. And one of the first things that I did when I had my own group was to make an undergraduate version of Alain's experiments, because I thought that everyone should be able to see this. Okay. Then John Clauser was at Berkeley when I was at Berkeley, so I got to meet him. I got to hear him talk about these experiments. And then finally, I had the good fortune to be involved in the experiments in 2015 by Anton Zeilinger's group. Okay, so the Nobel Prize is for these three people: Alain Aspect in France, John Clauser in the US, and Anton Zeilinger in Austria. And it's for establishing the violation of Bell inequalities, which in some ways seems a little bit strange that they put Bell, that's John Stuart Bell, that's the name of another person, they put in the description of what these people did, but that's completely appropriate because John Stuart Bell is so critical to the field. And of course, since he passed away in 1990, there's no way that he could be recognized directly. This is somehow an indirect recognition of his enormous contribution to the field. So even though I call this local realism, they had the good sense to put his name in the description. Okay. So this is what I would call the Wunderkommer phase of quantum physics. So this is, I need to tell you what a Wunderkommer is. So Wunderkommer is a German word which means chamber of wonders or room of wonders. And this is something that in the age of exploration, any noble or other important wealthy person had. So that's illustrated here. Ships were going out and exploring the far reaches of the world, and they were bringing back things which illustrated the wonders, the richness of life, but also minerals, fossils, things like this in the world. And if you were an important person in those times, then you would have one of these Wunderkammers. One, because it was a great joy to see all of the wonders that were out there in the world, right? And so that was the main motivation for having these things, okay? But also this evolved into natural history and classification of animals, and eventually gave birth to the theory of evolution, right? And then finally, this got these Europeans comfortable with the idea that there was a vast world out there and that their role in it was going to be an important role. So for better or for worse, this helped them get comfortable with the idea of empire, okay? And so I think that's somehow appropriate to the work I'm talking about today, because it was bringing wonders of quantum physics into the laboratory where people could see them for the joy of it. And indirectly, it's getting us physicists comfortable with the idea that quantum physics and these wonders are something that we are going to be interacting with in quantum technology. And I think that's, in some sense, the sense of this, pioneering quantum information science and clearing the way for new technology based on quantum information. Okay, so that's a Wunderkammer. There's another thing, which is that the best Wunderkammer ever made was made by the Emperor Franz I of Austria. And in 1750, he bought the best existing Wunderkammer from someone in Florence, and then at great expense he bought it, and then he invested still more of his riches in improving this, and his collection eventually became the Naturhistorische Museum in Vienna, which is an absolutely amazing place to go if you want to see the wonders of the world. So I highly recommend this to anyone who wants to see it, okay? So in the age of exploration, there was a great amount of resources from the state going to these wonders. And in fact, Anton Zeilinger in Austria also benefited from a good deal of resources from the state to bring the wonders of quantum mechanics into the laboratory and make them visible. Okay. So all of these topics were being developed. Experiments were being developed to make these visible in this time period, in the Wunderkammer phase of quantum physics. And then all of this stuff gets us ready for quantum technologies. Okay? So if you go to the Nobel Prize website, then you can see the scientific talks that were given by the laureates. And the talk by Anton Zeilinger is particularly good about this phase, both in the spirit and also in the content. He talks about lots of experiments that brought new phenomena out of the textbooks and into the experiments. Okay, and I'm going to show you one of these, but first, because of the way he speaks, I need to kind of tell you what he's talking about. Okay, so he started right after an experiment by Helmut Rauch, which developed this neutron interferometer. So this here is a piece of a single crystal of silicon. Okay, so that becomes available for electronics, and they take a big single crystal and they cut away the parts that they don't need, but they're left with a crystal structure here, here, and here, and they're all a piece of the same crystal, so that the periodicity here, the crystal here, knowing where the atoms here, allows you to know where the atoms here are here and here. So there's a spatial coherence in here, okay? And then they take this object to a nuclear reactor in France, and they send in a beam of monochromatic neutrons, and the neutrons hit this first plate, and by Bragg scattering, some of them get deflected and other ones don't. Okay, and then they travel a bit and they reach the next plate, and then they can again be deflected. Okay, and then when they come back, they again have an opportunity to deflect or not deflect. And so a neutron can reach this point by one of two paths, and they have an interferometer for neutrons. Okay. They put in a piece of aluminum here, and you might think that aluminum would block neutrons, but it doesn't block neutrons. It's transparent to neutrons, but it allows them to pass, acquiring a phase, and that phase depends on the distance, and so the relative phase between this path and this path depends on the angle of this piece of aluminum, and you can see here there's a pivot, and so that can be rotated. Okay? And so then looking at the neutrons arrive, and they see this neutron by neutron, because the neutron is an energetic particle and they can detect it, then they see this oscillation as a function of this relative path difference, and they see this oscillation, okay? And so this is something which you would predict from a textbook. Quantum mechanics says that neutrons should also have wave-like properties, okay? But this is now something that you can see, and it is somewhat wondrous that this is a neutral, massive particle that is behaving in a wave as a wave on a macroscopic scale. It's something that you can very clearly see, okay? So that's the background, and now Anton is going to tell you his role in this.
I was not participating in the development, but I had the idea in '75 to use this to demonstrate what is known as 4-pi spinor rotation. If you turn anything around by 2-pi, like me, turning around, I'm the same. If I were a neutron, I would have to turn around twice to be the same. It's the phase which is different.
Okay, so I think you get some idea of the joy, the wonder of this from the way that he presents this. And the talk is full of this stuff, and I strongly recommend that you go and find it. Okay. Okay, and in fact, this is something that you can find in a quantum mechanics textbook, that your state when your neutron is spin up is this, and if you apply successive rotations to it, it becomes spin down, but there's an I here. You apply more successive rotations, it's again spin up, but it's acquired a -1, right? And is that something that's physically significant, or is that just a global phase that we ignore in quantum mechanics? If you want it to get back, then you need to do the rest of the 4-pi rotation, okay? And in this interferometer, it is physically significant. So this is the same interferometer. The neutrons come in, they get split, and what they've done is they've put here a piece of iron that's an electromagnet, but it's going to apply a magnetic field just in this path and not in the other path, okay? And so then as the neutron, which has a magnetic moment, passes through the field, it's going to precess, and they calculate how much extra current they need in order to make it precess by 4 pi, and that in fact agrees with the width of, the period of these fringes. And so that shows that, yes, in the laboratory, you can see that something only really becomes equal to itself after it's gone around twice if it's a spin 1/2 particle, okay? So I think the emperor would have been quite pleased with that demonstration, and I think he probably would have given the money to get a reactor so that he could have this wonder in his Wonderkommer, okay? Okay, but the alligator, the biggest thing in the Wonderkommer is quantum non-locality, okay? So now I'm going to tell you about some aspects of this, okay? So this is a topic that many people have thought about, starting with Einstein and Niels Bohr back in the 1920s and going up to the present day, okay? So it's 100 years of history, almost 100 years of history of this topic, with lots of contributions from lots of people. Okay, and these are distinguished because they made experimental tests, and Bell here is somehow the pivot where he gives sense to the whole operation. So starting with discussions, completely theoretical discussions by the founders, which are essentially metaphysical discussions about what a physical theory could be. And then Bell turns that into an experimentally testable question. And then these people find ways to do the experiment. And then these people, I will say later, they, in some sense, perfect the experiments. Okay, so this comes from the uncertainty relation, which I think everyone knows. Just historically, the uncertainty relation comes out of the work of Heisenberg in matrix mechanics, and it comes out of Schrödinger in the Schrödinger mechanics. And Heisenberg was somehow a protege of Bohr, was under the protection of Bohr, who was one of the greats of the old quantum theory. So from 1913, the Bohr model. And Schrödinger was somehow a protege of Einstein, okay? And although the theory was done by Heisenberg and Schrödinger, the debate about what it meant was done by their bosses, by Bohr and Einstein, okay? So the debate, there's a lot to say about the debate. I'm going to summarize it down to 2 sentences, okay? So if you've ever tried to read Bohr, Bohr never said anything that was simple enough to put in a balloon like this. Okay, but my summary of what he said is that the understanding of this, the fact that knowing one thing means you can't know another, comes down to a question of what has meaning. So the classical concept of position has no meaning except in the context of a position measurement. And this allows him to escape many strange things in quantum physics, because he says all that matters is the measurement results, okay? And the rest of it doesn't even exist. There's not even a sensible question, does it exist? It just has no meaning, okay? Einstein, in contrast, is a strong realist. He wants everything to have an explanation. If there's a wave function, then there should be something real that corresponds to that wave function, okay? Einstein was very good at putting things into a few words. And he said, do you really believe the moon does not exist when you do not look? So that's a response to the ideas of Bohr. That's not something that he said to Bohr himself. But this stresses the difficulty with Bohr's position. Surely at some point there must be something real that we can talk about besides the things that we write down in our notebooks when we take measurements. Okay. So there was a long debate between them. The final in some sense, the final word in it was this paper of 1935 by Einstein, Podolski, and Rosen, where they ask, can a quantum mechanical description of physical reality be considered complete? Okay, and this was news. So this is an article which appeared in the New York Times. It says Einstein attacks the quantum theory, which is somehow true, that he was trying to say Bohr is wrong. Okay, they note that the argument was that it might be correct, which is to say everything that it predicts is correctly predicted. All the measurements are correctly predicted, but it's not necessarily complete. Maybe there's more information that could be had. Maybe we can know what's going on behind the scenes, and Bohr's claim that position doesn't mean anything is wrong. There is always a position. Okay. Okay. Then note that this date is 11 days before that date. So that means that somebody at Physical Review must have leaked to the New York Times that there was this paper and provided the text of the paper, right? Okay, now imagine being a quantum physicist at that time. You can read this in the New York Times, but you can't read this article yet. Right? This must have been an interesting situation. Okay. Okay, so I'm going to show you the Bohm version of the Einstein-Podolsky-Rosen argument. Okay, so this was done with position and momentum, and this is going to be done with spin or photon polarization. It's just clearer in this second version. Okay, so space-time diagram, time is moving upward in this direction. Space, there is a measurement station for Alice, a measurement station for Bob, and some source of photons, one of which is going to be sent to Alice and one of which is going to be sent to Bob. And we hypothesized that what is being sent is an entangled state, and this entangled state has a superposition of each photon being horizontally polarized or each vertically polarized, and mathematically that is the same as a superposition of both of them being diagonal and both of them being anti-diagonal. Okay? So that's what gets sent out. Alice decides to measure what she gets, but because it's one particle, she can only make one measurement of its polarization, and she has to choose either horizontal vertical basis to measure or diagonal anti-diagonal. Okay, so say she measures horizontal vertical, then that will collapse the state. She either gets an H, in which case all that's left is this part of the state, or she gets a V, in which case all that's left is this part of the state. And that describes not just her particle, but also Bob's particle. So Bob's particle, which before could have been H or V, and also could have been diagonal or anti-diagonal, now is either H or V. And a possibility has disappeared, two possibilities. It can no longer be diagonal and it can no longer be anti-diagonal, okay? Then Bob can make a measurement, and if in fact this state was prepared, then if he measures in the same basis, then we should have H on this side and H on this side, or V on this side, V on this side. They should agree if they measure in the same basis, okay? Okay, but there's something very strange here, that what Alice chooses to measure determines what Bob's state can be. Okay, but it gets weirder because I've ordered these so that Alice measures first and then Bob measures second. But to someone who's passing the experiment at high speed, due to the relativity of time frames, it's possible to reverse the order of these, in which case Bob measured first and then Alice measured. Right? So there is some spooky action at a distance, but we can't even say in an observer-independent way which direction the action is. Okay? So all of this seems crazy, right? And Einstein's proposal is, no, you just assume that each particle has some answer to some property which tells what will be measured, whatever Alice measures and whatever Bob measures. So it has to have an H-ness, V-ness, and a D-ness, anti-D-ness. Okay, and so that would be a possibility for one pair of particles. These are were called by Einstein elements of reality, and then the next particle can have different values for these. Okay, and so this is what are called hidden variables in the modern description of this. Okay, so so this is the situation after Einstein, Podolski, and Rosen. Then you have quantum theory, which has all of these objectionable features. It's intrinsically probabilistic. Einstein hated that. I don't hate that, but Einstein hated that. God plays dice in quantum mechanics. It has a measurement problem that what Alice chooses to do changes the physical reality, right? So we are now part of the theory, okay? It has a non-local wave function collapse. The wave function at Bob's site changes in response to what Alice does. It's observer dependent. The only thing it's got going for it is that it makes accurate predictions, right? Meanwhile, if you have a classical theory like EPR proposed, then it can be deterministic or not, up to you, has no measurement problem, everything is local, it's observer independent. If it can make accurate predictions, then this is clearly the better theory, right? Okay, so that's the question. Can a classical theory make accurate predictions? Okay, and that's what Bell contributes. Okay, so this is Bell in the early 80s. So what he has here on the diagram here is in fact a diagram of one of Aspect's experiments. Okay, so his first his observation is that in this situation where you have a source that produces two particles, you are going to analyze them. Now he's going to give more than two possibilities. So this is now a continuous variable to describe the analyzer setting, but there's still just two outcomes on Alice's side, okay? Same thing on Bob's side. And then it's an undergraduate problem to calculate the probabilities. And like everything in quantum mechanics, it gives you something which is sinusoidal. And so if you set the relative angle between these analyzers 0, then you could get that they are both +1, or you could get they're both -1, but they're always going to agree. Okay, so that's this point. And if you set them 90 degrees apart, they're always going to disagree. And to get from one to the other, then you have this curve, which is a sinusoid. Okay. And then he formalizes Einstein's intuitions. And he says, okay, any theory, so there's going to be a source that is going to carry something, this ADHV character is going to be carried by the single variable, which we're going to call lambda. Okay? And that's an additional piece of information that's available to Alice and to Bob. Okay? And then any theory has to provide this, a conditional probability, so that given settings A and B, it gives the probability for seeing the outcomes A and B, theta A and theta E. Okay. And then he insists on locality. So that means that that has to be a product of the probability to get A using only things which are present at Alice's side. And so in particular, the setting on Bob's side is not in this term. Okay. And on Bob's side, it's the same thing. This is the locality that the conditional probabilities has to factorize into something local on Alice's side and something local on Bob's side. Okay. Again, there's this hidden variable which carries the information about the particles. Okay. And then because we don't know what lambda might be, we have to give a probability to lambda and we have to sum over all the possibilities. Okay. So this is then a general framework. You put different functions in here and you have some theory that Einstein would agree with because it is local, that what happens here and what happens here are only involve things that are present there. It is realistic because everything has an explanation, because this lambda is something that you could know, even you could in principle know, even though you don't measure it. okay? And so this is local realism, okay? Then using local realism plus an additional postulate, which is setting hidden variable independence. So that means that the joint probability for Alice and Bob's choices about what to measure and the hidden variable are statistically independent. Okay, so that means that this joint probability factorizes, and this is a crucial point here. That means that your probability for theta A and theta B knowing lambda is the same as your probability not knowing lambda, which is to say lambda tells you nothing about what is going to be measured, okay? And similarly, what is going to be measured tells you nothing about lambda. So that's the statistical independence, okay? And this somewhat misleadingly gets the label choice. There's something called the freedom of choice loophole, which is when this condition fails, okay? But, okay, and then if you have these two ingredients, then you get Bell inequalities. And there are many Bell inequalities that are useful for different things. I'll show you the simplest one that I know, and that is used in the first experiment by Friedman and Clauser. And it simply says that a measurement with the relative angle of 22.5 degrees and a measurement with a relative angle of 67.5 degrees can be separated by at most 1/4 in probability. Okay, so that's the Bell inequality that they used in the first case. Okay, and that's what you would get if you connected perfect agreement with perfect disagreement by a straight line. Okay, and so then you can guess where this goes. Then since the actual probability or the quantum probability is given by this sinusoid, then if you look at those particular points, you see that the difference in probabilities is more than 1/4. Okay, and so in that way, Bell has demonstrated that quantum mechanical predictions cannot be reproduced by any local realistic theory. Okay, so he's answered this question, the question mark, is it possible for a local realistic theory to make accurate predictions? No, it seems that it's not, or at least it's not possible to make the quantum predictions. And so it's not possible to complete quantum mechanics with some extra information, which is what Einstein claimed in the EPR article. Okay. And now it's an experimental question. Does nature agree with local realism, which must somehow obey this straight line picture, or does it agree with quantum mechanics? Okay. So now I start talking about experiments. What time is it? 12:35. Okay. Okay, so the first experiment, most people don't know this. The first experiment was done at Columbia University by C.S. Wu, so very famous physicist for discovering parity violation. And she was a nuclear physicist, so she used the tools of nuclear physics to do an experiment. Okay, so she takes a source of positrons that come in from the left here. They get stopped in a block of copper, and this O is where they get stopped. And then the positrons very soon find an electron, and they form a positronium atom, which will be in an S state, so a rotationally invariant state. Okay, and then there will be positron-electron annihilation, which leaves nothing behind and produces a pair of photons which go out in opposite directions. Okay, and so sometimes those photons will go to this detection setup and sometimes to this detection setup. And the rotational invariance means that the total angular momentum of these two photons has to be 0. And that means that they're always going to disagree about their polarization. Okay? And she makes a polarization analyzer using Compton scattering, which is a polarization dependent process. And so one polarization can be scattered to the detector here, and the other polarization can be scattered other places, but not to the detector. Right? Okay. So this is the way it should work. It doesn't work very well. The reason is that Compton scattering is not a very good polarizer, and the polarization dependence is not complete. Okay, and so as a result, she sees a dependence on the relative angle, but it's not strong enough to violate a Bell inequality. Okay, and so that's the first experiment. Okay, and then the Friedman and Clauser experiment in 1972 is in some ways very similar, but it's done not with gamma rays. It's done with optical photons. So an atom, which again has two S states here, is excited into the first of the S states, and then it decays, emitting two photons. And because it had no angular momentum here, and it has no angular momentum here, it must have emitted two photons with no angular momentum. Okay. This is Clauser in Burge Hall, so that's also where I did my PhD. He was in the basement, which is the best place to be if you're an experimentalist. I was on the highest floor, which is the worst place to be if you're an experimentalist. Okay. And here he is assembling his system. Okay, so there's in here there is an atomic source of pairs of photons, and then this is a polarizer. So this is it's a good polarizer in the sense that it has a good extinction. One of the polarizations does not get through. It's also very large and heavy, and you can see it's on this rotation stage with these indexed stages, so he can repeatedly put it in different positions. And here's the detector. Okay. Here's Stuart Friedman in the same laboratory, and I love the wide colors here. This is the early 1970s, when you could go to the laboratory in the morning and go to the discotheque in the evening without changing your clothes. Okay. So as I said, there's an atomic beam. There is here a lamp in order to excite it. There are two polarizers. They have to be very large because it's very inefficient, and they have to collect a large solid angle in order to have a reasonable event rate. Okay, and then those detectors feed into coincidence electronics to tell them whether this fired and that fired at the same time. But note, there's only one detector on each side. Okay. And what did they see? So they're measuring this probability that they agree for a particular outcome, right? So do they see both detectors, both detections as a function of the angle here? Okay, and they didn't draw the line, but I draw the line, and you can see that they succeeded, right? And they use this Bell inequality. This R0 is the total rate that they see. This is the rate that they see with a polarizer in place. And you see that it is a statistically significant result. 6 sigma should be unquestionably, they have demonstrated a Bell inequality violation, and they have disproven local realism, right? Okay, but it's not so straightforward. Why is it not so straightforward? First, there were 2 experiments immediately after that got the opposite result. That they did something very similar, and they got a result that agreed with quantum mechanics. Okay, and this one was done at Harvard, and I believe it was never published, but Clauser knew of it, and in 1976, Clauser repeated this experiment to check his own technique and to see that it works. Okay. Okay, but there are a lot of experiments with different systems. Okay. The other reason that that's not final is loopholes. Okay. And a Bell test loophole is a way that an experiment could give you a violation of a Bell inequality with local realism. Or it's a way that a local realistic model could violate a Bell inequality. Okay, and so I will illustrate that. So this is a big, heavy polarizer, and it has to be rotated in order to change the settings. And so it's not crazy to imagine that rotating this big heavy thing, which is attached through this structure to the source of photons, that might have some effect on the source of photons, right? And if that does, then it would mean that we've broken the independence between these, because now the setting has an effect on the source and thus on the hidden variables. Okay, so that's a loophole here, that setting this might affect that. Okay, another loophole would be changing the angle here might have some effect on the remote detection setup by the same mechanism, that they're all connected to each other, right? That would be a violation of the locality assumption here. Okay, and so a local realistic model could explain this, okay, if you're willing to believe that this has some effect on those other components. Okay, what is a loophole? So I looked this up at some point. This is a loophole. It's the hole in a castle wall that they can shoot arrows out of. Okay, so the use of loophole, a loophole is some way to get around what otherwise seems like a clear proof or a clear law. Okay, and so you can imagine someone saying, well, I've surrounded my castle with this fantastic wall. No one is going to be able to cause me any problems. And then someone says, well, yes, but there's a loophole. And somebody walks up there with some snakes and pours them into the hole, or with some rats that are infected with a plague and into the hole. And so the person's fantastic wall has not actually protected them. Okay, this in modern parlance, in modern use, this is more like this. This is a joke from Calvin and Hobbes. Explain Newton's first law of motion in your own words. He's terrified because he doesn't know what Newton's first law of motion is. He gets a bright idea, which is to use his own words. Okay. Okay, so this is the first loophole closer, is Aspect. So this is in the laboratory. This is in the 1980s, around the time that these experiments were done. Okay, there are 3 experiments. The first one is really a copy of Friedman and Clauser. The main difference is that they had lasers available, and so they could much more efficiently excite this level, and so they had a much better event rate. And what they saw was data which looked just like Friedman and Clauser's, but with better statistics, and they acquired it faster. Okay, so everything is working. The technique is there. The second closes one loophole. So now instead of having one detector on each side, so they can detect one polarization at a time, they put 2 detectors, so they're detecting both polarizations together. Okay, and that closes a loophole in which changing this polarizer changes the brightness of the source. Okay, you could explain a violation here if you think that changing the polarizer angle changes the brightness of the source. You can no longer explain that here because you're able to compare ratios in all the time that you are taking data. Okay, and then the next loophole that's closed is the locality loophole. The locality loophole is the possibility, as I indicated already, that setting your analyzer has some effect either on the source, on the photons before they get measured, or on the measurement apparatus itself. Okay, and that's a question that you can address by space-time. So if Alice puts her analysis later, then it can be too late for the information to have an effect on Bob's side. Okay. And that's what this second 1982 experiment does. It has a source. It has here fast switches, and the switches can direct the photons either to this analyzer, which can have one setting, or it can deflect them so that they reach this analyzer, which has a different setting. And so now the condition of this switch determines which measurement is being made. Okay, and the switch was an acousto-optic modulator that could change in less than an acoustic period from diffracting, so that you make this measurement, to not diffracting, so that you make this measurement. Okay, and that is then sufficiently fast that this switch is changing before a signal from this switch could reach the other side, even at the speed of light. Okay, and so that is then some kind of guarantee that the choice of which measurement is made here cannot affect what happens on this side. Okay, there are many more loopholes. That's some portion of solving the locality loophole. There's still reason to do better. A random number generator was incorporated in 1998 by the group of Anton Zeilinger. I'll show you that in a second. It's important to detect almost all of the photons, because if you give the photon, the choice is not horizontal vertical, but horizontal vertical or don't get detected, then it can use that extra option to achieve a Bell inequality violation. Okay, so that was, so closing that was important. There are simple statistical loopholes. So it's necessary to do your statistics very, very well. And each of the experiments in 2015 had a dedicated statistician to do the analysis of the experiment. Okay, and then there's a loophole which doesn't really get its own name, which is the possibility that something influences your choice. Okay, and that's the one that we solved in 2019. Okay. So the thinkers, the first generation of doers, this group of people here were all closing loopholes. So Gregor Weiss used random number generators for the first time, and so closed the locality loophole. Mary Rowe used an ion trap to get very efficient detection, and thus closed the detection efficiently loophole. Thomas Scheidel did the first experiment that did something about the freedom of choice loophole. I'll show that in a second. Marissa Justina, the first experiment with high efficiency detectors with photons. So that's the same loophole that Mary Rowe closed with ions, but now she closed it with photons. Okay, so these people are all getting ready for the loophole free test, which is going to come in 2015. Okay, I just want to show this from Gregor Weiss, that they took a random number generator and it was very fast, and they used it with an electro-optic modulator to switch their analysis in the last moment before the photon arrived. And so now there's no longer time for this to propagate, and the choice of what to do is coming from some random physical process. Okay, the random physical process they used was to take a light-emitting diode, split those on a beam splitter, and have two photomultiplier tubes. And if a detection is here, then that's a 0. If a detection is here, that's a 1, and then that determines what is measured. Okay. Okay, so then we got involved in this in 2014, and we had these random number generators. We were approached by NIST in the United States, and they said, can you make us some random number generators, because we think that you can solve a problem that we have. And this is the problem that they had. So again, the space-time diagram, and they want to close the locality loophole, so the basis choice has to happen late, relatively late. The basis choice here is the actual manipulation on the experiment, and this star is the random event that tells you how you should change it. That's the random number generator operation. Okay, so they have to put that late. Okay, but now that there's a random event in here of physical origin, they're worried about something else, which is that if that is too late, then it might be influenced by the hidden variables. Okay, and that got the name the freedom of choice loophole in this article by Scheidel et al. Okay, so it can't be too late. And so that defines a time window in which it's necessary to produce a random event and then use it to make a setting. Okay. And then there's a new thing which came from the statisticians, which is that you have to know how much your setting could be influenced by something which happened before. You would like it to be influenced only by this random event that you included, but there might be some influence from prior conditions. And if there is, then that can influence your, okay? And this is the loophole that has no name. Okay. And in 2014, they gave us estimates for how well this had to work, and the extra probability that can be controlled by prior conditions had to be really tiny, 10 to the minus 4, 10 to the minus 5. Okay, and so this is something that had not been done in any previous experiment. Nobody had any number for how controllable prior conditions were, how much influence prior conditions had. Okay, and they also gave us ridiculously short time budgets, so 26 nanoseconds in order to do the whole job. Okay, and so that's what I solved. What's what I solved with a team at ICFO. So this is a photo of me and Carlos Abeyan, my student, going to Anton Zeilinger's lab. So that's Anton and Marissa Justina, who the PhD student who led the experiment. That's Soren Vengerovsky, the younger PhD student, who's now a postdoc at ICFO. And it just happened while we were there that we got a couple of famous visitors. And that's why the photo was taken. So does anyone recognize this person? People who have seen previous talk recognize this person. Okay, but this is the son of Fidel Castro, who is a physicist, was a physicist, and he's passed away. And he was in the neighborhood, and he knew that Anton Zeilinger was doing this experiment, and he called up Anton and said, "Can I visit your experiment?" So we had the son of Fidel Castro and the grandson of Fidel Castro come and visit the experiment. Okay. This is Marissa showing the son of Fidel Castro the entangled photon source. So this is, it's based on nonlinear optics. It's much, much more efficient than anything using atoms. Here's me taking the photo. Okay. And this is, Carlos took this photo of me explaining to a very skeptical Fidel Castro Jr. How the random number generator works, which you can just barely see here. Okay, so there is the random number generator itself. I will explain to you how it works. I hope that you like it better than Fidel Castro Jr. did. Okay, so this is, it has to be super fast. So this is done with telecom technologies. This is a single frequency laser diode, but it can be modulated at 10 gigabits per second. This is a photodetector, which is also very fast. It's a classical photodetector. It doesn't measure individual photons, but the flux of power that's arriving to it. We take the laser below threshold and then above threshold repeatedly. And so it emits pulses of light. In the time that it's below threshold, then the phase of the light inside the laser diffuses like mad. And so the phase that is produced in one pulse and the phase that's produced in the next pulse are extremely uncorrelated. They are effectively completely independent from each other. Okay. And then to turn that into a macroscopic signal, that goes into a Mach-Zehnder with a delay in one arm so that one pulse can interfere against the next pulse, and the relative phase becomes a power for the light that comes out, which is detected by the photodiode. Okay. So you can see this. If we don't have the interferometer, if we just put the detector here, then you see when it goes above threshold, then it does something crazy. This is relaxation oscillations, and it settles down. And this is the point where we can sample the voltage on the photodetector, and we see that it has a very low dispersion. This is a histogram of what you see here. Okay. When we put it into the interferometer, then we see the same thing in some sense, that it goes on and it does relaxation oscillations, but there's a very broad range, and it has this shape, which is called an arc sine distribution, which is the distribution of a cosine of a random phase. Okay, and so that's what we're seeing, is the interference of random phase pulses here. And the whole thing is super fast. And more important than that, we can say by measuring the imperfections in the system, how much effect could be contributed by other things that are not the phase diffusion of the laser. Okay, so I'm almost done. There were 3 loophole-free tests. So this one with Zeilinger's group, but this one at NIST, and this one in Delft. And then this is the paper describing how we did the random number generation. And these 3 are back-to-back in Physical Review Letters. They dedicated the cover to this. This is a picture of John Bell with the faces of people that contributed to the field over the years, some of them very old, some of them very, very modern. So Valdemar Amaya, who was part of our team and did the optoelectronics, is there. Carlos Abellan is there. I looked for myself. I really wanted to be in the beard, but I'm not. I'm up here in the hair. Okay, so there's a tendency to say that these are somehow the final word. They don't appear to be the final word. Anton continues to do new experiments. These go under the name of cosmic Bell tests. And the idea is to take light from some astrophysical source and use that to determine what you're going to measure. Okay, so this again is looking at the independence between what you measure and the hidden variables. Okay, and so by putting the experiment here and collecting light in one direction from some astrophysical source that in this case is 600 light years away, and this one here that's almost 2,000 light years away, then they can say that assuming that the photons that they saw traveled to the Earth without being disturbed by the hidden variables, then the only way the hidden variable could be correlated with these things is if the hidden variable itself was created hundreds or thousands of years ago and has been sitting around waiting for the experiment to happen. Okay, and then as Bruno mentioned, in 2016, we did an experiment and published it in 2018, where we used humans playing a video game to choose the settings. Those went into a mobile phone through the internet to experiments in lots of places, including NIST and Vienna, where they did experiments using human-derived randomness. And again, this is to look at whether we can achieve independence between the settings now generated by humans and the hidden variables. So assuming that these people were not being controlled by hidden variables, then we can have independence of their choices from the hidden variables. Okay, I think I'm out of time. There is a contribution to quantum technology here. It's quite large, that a lot of techniques that were developed for this Wonderkommer approach to see interesting things become useful for quantum technologies. And if you ask me about it, then I can tell you about a very, very direct input from this topic to quantum cryptography. Okay, so thank you for your attention, and I hope I've given you something to think about. And I'm
Thank you very much for the very nice talk. And now it's time for questions. Let me start with one myself. So, is the list of loopholes exhaustive, or can there be loopholes that nobody has thought about? Or
there's definitely not a proof that all the loopholes have been found. There is a loophole that was found in 2013. Well, there are two loopholes that were found in 2013 when the statisticians were brought in to work on them. The first of those statisticians is Peter Bierhorst, and he was one of the few people in the world that was really not convinced by all of the prior work and thought that Einstein must still be right. Okay, so I think I would say there is still a real possibility that someone who looks at this problem with a fresh eye will find something which has not been seen by other people.
questions?
So thank you for the nice talk. Maybe this is a very crazy idea, but have someone, I mean, it relies a bit on the philosophy more than science, but there is someone like considering that all these settings, I mean, all these reality equalities rely on whether this hidden variable is independent of the setting, right? So anyone consider whether these things that you're considering as a randomness, like having someone playing a computer and based on this movement decide the setting, has someone considered that there could be like a connection between this in principle randomness and the actual hidden values, like it's coming from some sort of initial conditions of the universe or something like that? Like there is like a machine in where everything is connected, and then you could not really disentangle that because like a fair assumption where these things that obviously for us looks like random are actually already set up by some initial condition thing, and this is somehow correlated with this hidden variable.
So this is a very good question, and it's something that is somehow runs through all of the work that I've talked about, which is I guess the old way to say it would be, what is reasonable to assume about a hidden variable model? And you look at the early literature and you will see the experimentalists say, we think it's reasonable to assume that this. They understand they didn't close all the loopholes, but they would like to say that the ones that they didn't close are somehow exotic hypotheses, right? Things that they could get rid of. And there's a trend, and now nobody talks about what's reasonable, what's not reasonable. They just talk about which classes of models have been eliminated by their experiment and which have not been eliminated by their experiment. Okay, and then your question, could there be some model in which something very far in the past, maybe with this cosmic Bell test, maybe 2,000 years in the past, there was something which coordinated the behavior of some stellar, not stellar object, but some astrophysical object, and what's going to happen in the experiment, which involves some photons that are produced by a laser interacting with a crystal, right? So that's definitely a possibility, and they look to see what possibilities remain and what has been excluded and what has not been excluded. Is it a reasonable thing? I think the professionals in this say that's for the audience to decide. That we can tell you what we've eliminated, and you can decide whether you think we've eliminated your favorite theory or whether you are convinced by what's been done.
I was late, so maybe you mentioned this term, but I think you were referring to this thing in foundations of quantum mechanics called superdeterminism. And it's basically this idea that everything is correlated in a way that these experiments are providing these results which just apparently violate locality. But the people also complain that if one assumes that there is such a superdeterministic, superdeterminism is true, then there would be a problem with science in general, because one of the basic assumptions is statistical independence when one is working in experiments, for instance. So I don't know, maybe you could say some words about this, because for me, it's in my head, it's also quite vague, all this issue about superdeterminism.
Okay. Right. So this is something which has been in the literature for a long time, and the term superdeterminism comes from Bell himself, and it refers to the possibility that everything is determined by something that happened before, which is determined by something that happened before, which goes all the way back. Okay, and it's not difficult to prove with the statistics that you cannot do a Bell test under that condition. That you need there's an independence assumption, and you don't have independence if everything depends on everything that happened before, right? Okay, so if you believe that everything is deterministic all the way back to the beginning, then none of this is going to change your mind, because none of it is relevant to that question. Okay, so that's the super deterministic position. And then there's a philosophical question. Is that compatible with everything else that we believe about the world? You know, we think that we have free will, but if everything is determined, including us, then we don't. So can we make that compatible? And philosophers argue about this forever, whether it's compatible, that determinism and human thought and such. I'm not a philosopher, so I'm not going to be able to illuminate very much there. There is an interesting quote from Einstein, so something that he wrote to a friend, where he's talking about what kind of God he believes in. And he says that he believes in something like Spinoza's God. And Spinoza is the philosopher who most strongly made the argument that everything is deterministic. So it's possible to read that as saying that Einstein, at least when he was writing that letter, believed in superdeterminism. And if that's the case, then none of this would convince him.
So since I don't see no more questions and we don't want to argue forever like philosophers, I think it's a good moment to stop. Thanks, Morgan, again, for the nice talk.